Are we ready? Creepy screen is up. That means it's time to begin. So I learned an important lesson on Monday about copyright infringement. No, seriously. Shortly after class, I got an email from YouTube saying my class video had been banned because it included copyrighted content. Turns out you are not allowed to play YouTube videos within your YouTube video. Even though I played the ad for you ahead of time, right? I had to get special permission. So after 2 days of fussing with the video to try and edit those parts out, I believe the video is now eligible to be played. What I ended up having to do is take out the end, which is the part where the first copyright issue was, because I let it go full screen so you couldn't tell it was a YouTube video. And so the people who made the video were like, you can't do that. So I cut out that part. And then I had to go into the part where I let it play, or I was doing other things, and I had to take out the audio. So there's like a 4 or 5 minute chunk where the audio repeats because it just borrowed audio from the front of the recording, and it doesn't match at all while the video is playing in the background. So normally before this lecture, I like to play a little bit of the Karate Kid as a background to like illustrate this, and I'm not going to do that either. So YouTube is easy until it gets very picky with you. But there's a YouTube video on the Karate Kid that illustrates this concept here, which is why we're temporarily going backwards in our material. So what is this class about? Someone tell me. Big picture. What's it called even? Turn this down. Not a trick. Multi-level? What kind of multi-level specifically? Longitudinal, yeah, and repeated measures is the other word in the title, right? So up to this point, we've been talking predominantly about longitudinal models, right? Model for the means, model for the variance. The new stuff relative to models you have seen in the past is all about random effects, right? That's the new part, as well as other patterns of variance and covariance. So we're at the point now where we've started putting in predictors, meaning fixed effects of time, polynomial effects of time, piecewise effects of time, and nonlinear functions of time in the last class. And we're just about to start putting in more predictors that aren't related to time. Time invariant predictors is the next unit. Through several years of trial and error, I have discovered that folks after their standard introductory graduate stats courses are not ready for the interactions part of the equation. So I always step backwards, sometimes at the beginning of the course, and this time I'm trying it right before the relevant material, to talk about just the linear models concepts of interactions as a first pass. The analogy from the Karate Kid, do you guys remember this movie? Ralph Macchio, like 1984, great movie. So there's this point where his training mentor trying to teach him karate, in exchange for teaching him, makes him do household chores, right? So he has to wax the car, wax on, wax off, paint the fence, sand the floor, right? And he's doing all these things every day, and he's getting increasingly frustrated that he came here to learn karate and he's not learning karate. And then there's this great scene where he's like, show me sand the floor. He's like, hua, hua, hua. And he shows him that all these motions that he thought were just arbitrary cleaning tools were actually karate. So I'm showing you the cleaning tools, but I promise you we're going to do karate, okay? That's where I'm going with this. We're stepping backward to talk about regression for maybe 2 weeks, because I need you to learn this stuff in a way that you may not have learned it before. If you have learned it this way before, great, but you're in the minority. So in all the classes I've taught and all the workshops I've given, this has been the part that people stumble over. So I want to go back over it to make sure that that doesn't happen to you when we start trying to combine the idea of random effects with various kinds of interaction terms in the fixed effects side of the model. So that's my precursor for why we're doing this. So this material actually comes out of chapter 2 of the textbook. We did the beginning of chapter 2 at the very beginning of the semester, just reviewing the idea of a linear model, how to put in continuous predictors, how to put in categorical predictors. We're going to do interactions this week among continuous predictors first and then categorical predictors second. So the reading that goes along with this is section 2 in chapter 2. All right. Before I dive into this, any questions on anything else that's not this? All right, then away we go. No copyright violations today. Unless they get mad at me for talking about the Karate Kid, in which case that's a level of Big Brother I never would have anticipated. So interaction terms is the topic, because almost every kind of fixed effect we're going to start interpreting in longitudinal models is going to be an interaction of some kind. So you got to know what to do with them. So interaction is the idea of moderation, not mediation, but moderation. When you have two variables that interact, you could describe one of them as moderating the effect of the other. Which variable is the predictor and which variable is the moderator is a completely substantive decision. Statistically, you can talk about it either way and it's equally correct. So the reason that some of this doesn't get taught has to do with how we parse up general linear models into different courses, I think. So if you took a class on ANOVA, or you open up ANOVA software in SAS or SPSS, for instance, the default specification when you enter in all of your fixed factors is all possible interactions. So if you have an experimental design where you have 5 different dimensions, so you have like a 2 by 2 by 2 by 2 by 2, something like that, when you put that into an ANOVA, you get everything up to the 5-way interaction by default as part of the model. And typically you only talk about the parts that are significant, but you don't change what the model has in it. It stays this big, full factorial specification. In ANCOVA, you may do the same thing with the exception of the covariates. If you have in a continuous predictor that you view as a covariate, in an ANCOVA model, the definition of it is that the covariate has only a main effect. You've covariate out on the intercept, but not on anything else. Of course, you could put in interactions with everything else, but then you couldn't call it ANCOVA anymore, which is fine. In regression, though, a completely different default pattern of behavior is usually endorsed, in which you put in main effects of predictors, and maybe you put in interactions, but maybe not. If you put in interactions, it's up to you which ones, how many, what order they go in, and so forth. And in regression type software, you typically have to create the interaction term variables yourself as observed variables. So for instance, you would have to make a new variable called XZ interaction out of the multiplication of your 2 predictors. So I think given that these models are more like regression than anything else, the interpretation of interaction terms is a little bit trickier because people haven't had as much practice with it. So that's what I want to do. So main effects of predictors within interactions, they stay in the model. The same was true when we had a quadratic effect of time. Linear effect of time stays in the model. When people try to interpret interaction terms, most often what I hear them stumble with is they start talking about how the interaction changes the outcome. But that's not what it does. An interaction term changes the main effects. The main effects then change the outcome. An interaction term does one of 4 things to its constituent main effects. You've heard this before. Can you guess what I'm going to say? Okay, this is going to be one of those classes where I want to pause, let everyone think of the answer. I'm going to say an interaction does one of 4 things. It makes its main effects more positive, more negative, or less negative. Those main effects then change the outcome. Because of this, we can't talk about main effects just calling them that anymore. Once main effects are part of an interaction term, they become conditional. So this was the language that showed up in your very first homework assignment. Do you remember this? Simple main effects versus just main effects. If a predictor does not interact with any other predictors in a linear model, it's just a main effect. It's marginal. It's unconditional. It's the main effect for everybody, all the time. If a predictor interacts with another predictor, then we talk about it as specific to the interacting variable being 0. It's conditional. So if I have this model here with predictors of W, X, Z, and X by Z, W is a marginal main effect. It's the effect of W regardless of what your values are for X and Z. The effect of X is specific to when Z equals 0, but unspecific with respect to W. The effect of Z is specific when X equals 0, but unspecific to W. So what you get out of a model then, you have to know what these things mean in order to interpret them correctly, and then what to do with the interaction term. A point of confusion frequently with respect to this language of conditional. In regression, whenever you put in multiple predictors into a model, you're taught to say, this is the effect of W, for instance, controlling for X and Z, right? That's the idea of a unique effect. All of the common prediction is factored out, and you're talking about this is the effect of one variable controlling for the others. That is always true. I'm talking about an additional level of conditionality, not just controlling for, but specific to. So if I have this model here, this effect of X is specific to when Z is 0. It's also controlling for Z. It would be a different coefficient if Z were centered someplace else, such that 0 was a different number, but it would still be controlling for Z. So we're talking about conditional on a particular value of the interacting predictor, not just controlling for it. We're always controlling for it whenever you put in multiple predictors into the same model. So I'm using the term linear model and regression somewhat synonymously. Let me clear that up. Linear model to me means model for the means. Fixed effects. Regression is a very specific kind of linear model that has a single residual variance, right? It's 1E. So linear model is just model for the means. That means everything I'm talking about applies whether or not you have a regression model, a multi-level model, a structural equation model, any other kind of model where there's fixed effects of predictors, this stuff goes for, okay? With me? All right. Questions so far while I reload? Diet Mountain Dew for those of you who are not watching at home. Austin, sir.
So for W in that model, would you say that all holding like X and Z constant, and then both of them are at 0?
Not at 0, but just constant. Yep. Because if you put X and Z onto a different scale where 0 meant something else, you'd get the same coefficient for W. Good question. All right. So why centering matters? Have we done this slide before? Does this look familiar? No? Okay, good. Well, then we get to have a little audience participation here. Let me record when I'm going to start typing here. So let's say that we have a linear model. In this case, it would be called a regression model because I have a single E at the end. That's the world we're living in this week, is just cross-sectional regression, just to get the linear model side of the story down. And I have an outcome of student achievement GPA on a 0 to 100 scale. X is a Likert scale type variable, parent attitudes about education, where the scale goes from 1 to 5. And Z is father's education level measured in years of education. So those are my variables in the story. I have not centered them in any way. So the range that you see up here is as they are in the model. So let me tell you what each of these things means as a consequence of the scale of these variables. So an intercept, we always know that as the expected value of y when x is 0, right? So expected GPA when attitude equals 0. What kind of person is that for? Can I have an attitude of 0 on a 1 to 5 scale? No. And ed equals 0. What would that mean? Someone's father never went to school, not even first grade. Maybe kindergarten. Would that be 0 years? Depends on where you start counting, right? But point being, it is unlikely, or maybe even impossible, that that predicted value could logically apply to anyone in my sample. That's like staring at the map of an airport and the "you are here" sign is like in another terminal. Like, it does you no good because it's too far away. There's nothing wrong with it, but it's kind of weird. Now, beta 1. Beta 1 is the slope for attitudes. So we say GPA goes up by 1. That's my coefficient. For every unit up in attitude. Am I done? I put dots, so that's an indicator of to be continued, right? Aaron, what do you think I should put there?
Well, the education is constant.
It would be held constant if this were just a main effects model. However, say it again? At where? At 0, yes. When ed equals 0. So now, in addition to my intercept being impossible, I have described the effect of attitudes amongst people who likely don't exist in my sample. I am 0 for 2 in meaningful coefficients. Likewise, GPA, the gap, goes up by 2 for every unit up in ed when at equals 0. I have described the slope of education for people who cannot possibly exist. 0 for 3 in terms of numbers that mean anything. Beta 3 is my interaction term. So I need to describe it as either affecting the slope for attitudes or affecting the slope for education. If I use attitude as the moderator, then it affects the slope of education. So I would say ed slope becomes, which pattern is this? I've got a positive main effect and a positive interaction term. This is a more positive as at up there. That's my short. Make sure it stays on the slide, but you can fill in the real words at your leisure. So the ed slope becomes more positive by 0.5 for every unit up at. I'll make that a little better. It doesn't fit on a line, but I'm doing what I can. So note that I didn't talk about GPA. I talked about the main effect of one variable changing as a function of the other. The education slope becomes more positive for every unit additional attitude. Likewise, if I go the other way, at slope becomes more positive by 0.5 for every unit up ed. There. What if this were negative? How would my answer change? Less positive for both, right? Because these are both positive. What if my attitude slope was negative? This one right here, right? At slope becomes, what would I call that? I call it more negative. But note, I didn't change this one because this story is about the ed slope, and I haven't changed that one yet. make sure that those don't get kept. So if I wanted to come up with a predicted GPA for someone who could actually exist in my sample, such as has a mid-range attitude and a father who graduated high school, my linear model's equation would give that to me right here, even though 3 out of the 4 coefficients don't really make sense. That is to say, you can center these variables or not center them anywhere you want. It's not wrong. The model will fit the same, it will generate the same predicted values. The rationale behind centering is so that the main effects and the intercept actually mean something. It's an interpretational decision. So not centering creates effects that are not necessarily wrong, but they can be very weird. Okay. Any of that you want to hear again before we move on or ask questions about? So one of the reasons that your current homework assignment I think is going to be a little challenging is because I'm trying to get you to think about not just the model and what it spits out by default, but all of the things that it predicts in doing so. How you can rearrange the parameters to get different pieces of information out of the same model. So let's do a little bit of practice with that. So here's my same equation. Not yet centering the variables, still working with them in their regular form. I want to teach you then how to generate new main effects from these models that have interaction terms. And you've seen this before, but I'm going back over it because our quiz last time didn't go so well. So we need to go back over it, I think, and it wouldn't hurt. So the first step here in figuring out how a model predicts any conditional main effect, you have to figure out what effect you're looking for and what all modifies it from the model. So for instance, if I'm interested in describing the effect of attitudes for different kinds of people in my sample, what I'm interested in then are all the terms that have attitude in them. Beta 1 is the conditional main effect of attitudes, and then attitude by education is the interaction term. If I take those two terms now, any estimate statement that you would write as to what the effect of attitude should be should only include these two things. The intercept is irrelevant. The main effect of education is irrelevant. If what I want to predict is the main effect of attitudes, only terms that have attitudes in them go in my estimate statement. No fewer, no more. So I take those two terms and I factored out attitude. Pulled it out of each term, stuck it out front. So what I'm asking for then is my new coefficient for attitude, which is a linear combination of its conditional main effect and the interaction for how it changes as a function of attitudes. Then we can calculate what the model says the main effect of education would be, or excuse me, the main effect of attitudes would be for any level of education. How do we calculate it? I'll give you 3 options in order of least to most painful. So the logic of it here. Let's say that I want to figure out what my new intercept and new simple main effects would be if I had recentered my variables to redefine where 0 is so that 0 refers to an actual person that exists in my study. Generally, people center their predictors near the middle. It could be the grand mean, it doesn't have to be. Middle is usually good enough. Sometimes minimum or maximum makes more sense depending on what you want to do with it. So we already figured out, based on just this model here, that when attitudes are 3 and education is 12, the predicted GPA is 75, so that's our new intercept. I'll type that in here. Now, what is our new slope for attitudes going to be? Well, I need to take this equation and figure out how it tells me what the slope of attitudes is going to be if education is recentered at 12. So here's my 2 terms that describe how the slope of attitudes comes to be. I factor out attitudes out of both, and I plug in what the model says. So previously, the slope of attitudes was 1. I want to know what it's going to be if education is 12, so I need to add the interaction coefficient times my new value of education at 12, and that works out to be what? Yeah, 7. Likewise, opposite direction. To figure out what my new slope of education is going to be, I need to know what it would be if attitudes were 3, which is my new 0. So I pull out the 2 terms that describe how the education slope comes to be, factor out education. I know that it was 2. I need it when attitudes is 3, so it's 3 times the interaction term. What is that? Yeah, 2.5. 3 times 1.5.
1.5 plus 2.
Oh, plus 2. Sorry, I was going the other way. My bad. 3.5. Yeah, see, this is why I don't want you doing math, and I want you writing estimate statements. Then you won't have to have this discussion with yourself about how to do second grade math. Because I only have so much room in my head, and to learn this stuff, some of that had to go, right? Now my interaction term. Same logic. I pull out any terms from my model that have both attitudes and education, and lo and behold, that's it. There's only one term. Another way of saying it is that that two-way interaction is unconditional. So regardless of what my centering is for attitudes and education as main effects, the interaction between them is always going to be the same. How are we doing? Okay, did you get taught this at some point in your lives? You did, Lucas? Who taught this to you?
Well, Chen 1 here and Robert Kovac
They made you do this? Okay, did they make you write estimate statements to do this? Okay, so that's the new part then, right? Who else? Does anyone get taught this before? I want to know. The same class as him, but did you get taught Lincom statements to do this?
First I recall seeing Lincom statements is in your pile of variance.
Okay. Anyone else get taught this? Amy did? Who taught you this? So somewhere else, again, your previous school, did they teach you estimate statements too or anything like that? Like recentering to get this stuff? Okay, so they taught you a more harder way than I'm going to show you, but still a way to do it via software. Yeah, that's how I learned it too, by the way, is you recenter to get the new versions of the main effects. But that becomes cumbersome if you want lots of them. So, yes. Anyone else? Yeah, you got, who taught you this? Jonathan. That doesn't count. Yes, he taught you this because we've been working on our course materials together, and we both decided that this needs to be part of your thing. So who's never done this before? Raise your hands. Be proud. See, this is why we're going over this, right? Even if you've seen the logic of interactions, most people haven't seen the programming statements to try and decompose the model. So this is why we're going over it. This will be old hat by the time you have to do it for longitudinal data. So to get your new main effects out of any interaction term, which can help you describe the pattern of the interaction, you need to know the new term plus its standard error. So we can figure out these things algebraically for the estimate. The standard error is a little trickier. So here's 3 options to get the standard error in least to most painful. Ask the software to give it to you, and here's my list of options in different programs. And there's something in R, what was it, GLM something? GLM something in R you can add to this list. That's one option. Recenter your predictors. That's what Amy was taught, what I was taught as well. And hand calculations. Just saying, this is what the computer is doing for you. The formula for the new standard error is a function of the standard error squared for the simple effect plus the standard error squared for the interaction term plus twice the covariance between the standard errors for the two fixed effects. It's a thing, point being. That's what the program is doing for you to get the standard error. I don't ever want you to do any hand calculations. It's bad enough that I occasionally make you type things into Excel. Agreed? This is why I try and give you macros for things. So here's what we would do to get everything that we just did out of SAS or any other program. The Piles of Variance website, by the way, has all this. This is from Chapter 2. The examples from Chapter 2 we're going to do has it in all the packages, so you can download to see what this would look like in anything else. So here's my model. In ProcMix, this is just a regression model in this example, so I don't have any randoms. I don't have any repeateds because the default repeated is just E only, constant variance, and no covariance across observations. I have a fixed intercept by default, main effective attitudes, main effective education, and their interaction term. So note you can define interaction terms on the fly with an asterisk. Another thing that you can do, which I haven't taught you yet, but I will show you very briefly. Oh, come back. This is helpful if you have lots of interactions. Do this. If you put a bar between them, that's the thing that you hit shift above the enter key. It's a straight bar. This means give me all possible main effects and interactions among these variables.
Even if I have more than two? Even if you have more than two?
If I had more than two, it would look like this. That would give me all possible main effects and interactions up to the three-way. If I only wanted all possible two-way interactions, I would go at 2 instead, and it would do that. So there are various ways in SAS syntax to shorten it. There's some of this in Stata 2. I think it's hashtags or pound signs for those of you who are over 30. I don't think there is an SPSS though, but I tend to write out everything like this just to be clear as to what exactly we have in the model. So if I wanted to create a predicted GPA for any level of my predictors here, so right now we're in the uncentered predictor world. Do you remember what I told you the words refer to here? When you type words in these statements, what are you asking it about? The coefficient, the fixed effects. So when I type intercept 1, I'm saying I would like 1 beta 0, please. You're at a drive-through window. Just think of it. You're making your order here. I'd like 1 beta 0, please. And if attitudes is 3, let's see here. Yeah, this is there's a typo in here. Hang on. Yeah. I went back and forth here. So if we use this version of the model right here, right? What goes here? 3 and 12 and 36, 3 times 12. Yep. I had gone back and forth between my centered and uncentered versions, apparently. I apologize for that. So the effective attitude, if education is 12, that one's right. Let me mess with the spacing here. And the effect of education, if attitudes is 3. Yep, those two are right. Okay. So the bottom 2 lines are asking for simple slopes. They're asking for conditional main effects, specific main effects at levels of the interacting variable. Note what is not in these 2 lines. Intercept. If you are asking for a slope, intercept does not go there. Intercepts only get included if you're asking for a predicted outcome, a predicted y. So if we want the effective attitudes if education is 12, I am pulling from this line right here with attitudes sitting out in front. So I need 1 beta 1. That's what at 1 means in this second line here. I don't need any beta 2s because the main effect of education does not contribute to the main effect of attitudes. It's the interaction of attitudes and education that contributes. And if I want to have education equals 12, that's why the 12 goes there. So if I look at the, let me see here. If I look at the composition of this line, I've already said that wherever you see attitudes, put a 1 there. So what I'm saying is wherever you see education, put a 12 there, and 1 times 12 is 12. Likewise, if what I want is the effect of education, that's this term right here. So I don't need any beta 1s. I need 1 beta 2, and I need 3 beta 3s. So even though both of these lines end in the same two-way interaction, the value that is put after it refers to which one is the moderator for this particular statement. The first statement is asking about the slope of attitudes. The moderator is education, so education gets the 12. The second line is asking about the slope of education, so attitudes is the moderator, and the interaction term gets a 3. So getting these things right really is 2 different steps. Number 1 is to recognize what all terms go in the line. And whenever you are requesting a predicted outcome, it's everything. The entire model contributes to predicted y. Any term that you omit, you're saying it's 0. If that's what you want, go ahead and omit it. But otherwise, it's being held to 0. Whenever you are asking for a predicted slope, every term in the model that has that slope in it gets put in, but no more. So I included these zeros for pedagogical purposes. I wouldn't have to include them. I'm trying to make the point that the main effect does not contribute to the other main effect. Questions? So we'll do some more practice in getting the right values. So if what I'm asking for is predicted GPA, then I need everything in the model. And what would I put here? If I want the predicted GPA when attitudes is 5 and education is 16. And now note I'm in the centered version here. I want 2. And what do I put here? 4. So these are relative to the new zeros. 5 is 2 more than 3. This is part of the second grade math I do remember. That part's still in there somewhere. So what do I put here? 8. Yeah, is that third grade? Is that still second grade? Anybody know? No? Okay. Hell, these days it may be kindergarten. I wouldn't be surprised if my 2-year-old knows this. He can already work the Roku better than I can. All right, attitudes of 1, what do I put here? -2, yes. 1 is 2 less than 3. What do I put here? 0. That means, what do I put here? 0. Negative 2 times 0 is 0. And this one, 0. And this one, 8. And this one, 0. So if you wanted to make a picture to put in a poster or a paper or something like that of what your interaction is, this is how you create the predicted values. Not only does this process give you predicted values, which is something you could do with a calculator or Excel, but it gives you the standard errors around them. So if you wanted to do any kind of like confidence window thingy around your predictions, the standard errors come right out with which to do that. Now, some more practice. Predicted slopes. Note that I've tried to help you out here. Intercept 0 for all of these things because we're predicting slopes, not predicted values, not intercepts. So if I want the attitude slope if education is 10, what goes here? A 1. Likewise, 1 here, right? Same reason. Back in my centered equation here, what goes here for the main effect of education? This is not applicable. The main effect of education has nothing to do with the attitude slope. But what goes here after the interaction term? Negative 2. Yep. And what goes here if education is 18 instead? 6. Good. Now down here, if I want the ed slope, is the main effect of attitudes relevant? No. Is the main effect of education relevant if I want the main effect of education? Need one of those. At the minimum, right? At a minimum, I need one of those. Now, if I want to have what it is at attitudes equals 2, what goes in the interaction term? Negative 1. Now what goes in the interaction term? 2. Yes. So illustrating again, what goes in the interaction term depends on which variable you're saying is the moderator and which variable is the slope. If you're asking for attitude slopes, you fill in education values. If you're asking for education slopes, you fill in attitudes values. But if you had a significant interaction, these types of statements will help you explain it. You can talk about at what level of attitudes the effect of education is significant, for instance. And for what level of education does attitudes matter or not? All right. One more example of doing this here, setting up the idea of regions of significance, which I'll be really surprised if anyone has taught you. So if I have a model that looks like this, and this is heading into, I think, one of the examples from Chapter 2, I have an effect of age centered at 85 because my example has old people in it. I have the effect of gender in which men are the 0 and women are the 1, so I'm calling this the effect of being a woman. And then I have their interaction term. If I want to know what the age slope is for dudes, what goes here? Is the main effective age relevant in asking for the main effective age? Yes, at the minimum I need one of those, right? Is the main effective gender relevant in asking for the main effective age? No, don't need this one. Now, if I want the age slope for dudes, what do I type here? Dudes. Yeah, right here. 0 equals dude. And age slope for, what's the analog to dude? I want to say chick, but that's maybe not right. Can you come up with anything less offensive? Can I say dudes and chicks? Dudes and ladies? I don't know. Oh, that's good. That's good. Dudette. If you want an age slope for a dudette, what do you type here? 1. Can you think of any other age slopes that I would logically want to find out about? if I live in a world where gender is binary? I can't think of any. If that's all the information I have, then that's it. So if I have a categorical predictor interacting with a continuous predictor, I can get the slope of the continuous predictor for each category. So I could say, yes, there's an age slope for men, or no, there's an age slope for men, but there is one for women. Or I can say there's age slopes for both of them, but the slope is more positive for men. I can say various things like that because there's a limited set of possibilities there. If I go the other way, though, if I want to talk about gender differences, is the main effective age relevant for the main effective gender? No, not this time, pal. How about the main effective gender? Need one of those at the minimum. So if I want the gender difference at age 80, given my model here, what do I type? -5, and if I want it at 90, what do I type? 5. And I don't have to ask what it would be at 85 because that's the one thing I'd get on the output already. Can you think of any other ages that I might want to know the gender difference at? Like 86, 87, 88, 88 and a half, like all of them, right? So Amy, do you want to recenter like for every possible age that you have and rerun the model? Neither do I. Do you want to write out like an estimate statement for every possible age and write it here? No. For this type of situation, there is something else you can do that may be more useful, and it's called regions of significance. This is in Chapter 2 and Chapter 7. So I give you some citations for this in Chapter 2. It's an old idea, but it's come back in recently. I want to say Chris Preacher and maybe Dan Bauer and Patrick, I don't know who all has published these things. I've got some references in there, but they took a twist on an old idea to come up with this. So rather than asking what the gender difference is at each age, we can find the ages at which the gender difference shuts off and turns back on again. Because we know that an interaction means non-parallel lines. At some point, your non-parallel lines have to cross. So let's say we have an interaction. Oh hell, let me get out paint. That works better than my markers anyway. There, let's get out my friend paint. Here's my y-axis and my x-axis. My x-axis is going to be age. There's my A for age. And let's say that my interaction looks like that. There's a positive age slope for one group and it's more positive for the other. If I want to talk about the gender difference, I could talk about the gender difference here, or here, or here. And I know that based on this model, any further age to the right of my x-axis, there's probably going to be a gender difference, right? It just keeps going and going and going. What's going to happen as I move to the left on my x-axis? Yeah, at some point, there's no gender difference, and then it's going to cross and go the other way, and eventually, if I went far enough to the left, there'll be a gender difference in the opposite direction. So what this technique allows you to do is find the boundary ages at which this difference becomes significant, at which the difference becomes non-significant, and at which point, if you've continued this pattern, it becomes significant the other way. And then you can talk about those boundaries in relation to your actual data. Like if you don't have anybody that's clear to the left of the x-axis, you can be pretty sure that there are no cases in which the opposite gender effect would be predicted. So you can compare those boundaries to your sample and see what it says then about the expectations based on what you actually have. So to do this, you need to request an extra piece of output that is called the asymptotic covariance matrix. In SAS, it is an option called COV-B. I think that's what it's called in almost all the programs, or some variation of it. But this is the word that you should ask the Google about to try and find this thing. So what it does basically is take this idea of a t-test for whether or not the slope is significant and work backwards to figure out at what point the ages, or the ages at which the gender effect is significant, and it could go the other way if you had a continuous predictor as well. So for instance, I worked out the math for this example that I have in Chapter 2. Here's my model. This model gave me a beta 2 for a gender difference of minus 0.53, and that's specific to age 85. The variance of that beta 2, that's its standard error squared. That is going to be on the diagonal of this extra matrix. The main effect of, the interaction term is this coefficient right here, which is unconditional because it's the highest order term in the model with respect to those predictors. The interaction standard error square is this, and in that COV-B matrix, I found the covariance of the beta 2 and the beta 3. So I know this is somewhat confusing because we're used to talking about covariance as on the variance side, but this is actually the covariance of the fixed effects that this is referring to. Because it's like what beta 2 is related to what beta 3 could be. So it's like of the realm of possibility of these betas, how do they go together? That's what this covariance matrix tells you. So based on the main effect, the coefficients from the model, their squared standard errors, and the covariance of the coefficients, you plug those into this formula that they gave you. And yes, I made you an Excel spreadsheet, and I made you a macro. You're welcome. Because lest you think I hate you, I'm trying to make your lives easier. And you plug in these numbers, and you end up with this range here, 60.16 to 79.52. Excuse me. So in terms of interpretation, we know that the gender effect is negative at age 85. So long as you are above this cutoff of 79.52 years, you have a significant negative gender effect. It's non-significant between this area, and it becomes positively significant below 60. So women are lower on this outcome after age 80. They're equivalent to men between 60 and 80, and they're higher than men before 60. In my sample of admittedly fake people, but nevertheless, I don't have anybody below 60. I think my youngest person may have been like 65 or something. So I would look at what proportion of my sample is in each of these ranges, and I can talk about, yeah, for half of my sample, because half of them are above 80, there's a gender difference, but for the other half, there's not. So rather than writing a million estimate statements or rerunning the model a million times, you can do one computation that tells you at what point on the continuous predictor the other predictor turns on and turns off. So I think this is handy. Do you like it? I think it's cool. Can you pretend? I think it's cool. Someday maybe you'll like it. So, maybe. So you feeling good with this? Yes. It may not be a possible value, but if it's a linear model, it's parallel lines. So there's always some region in which they're crossing. Yep. So in Chapter 2, I do this with age and grip strength, and then you would have another set of them. So this would give you like the ages at which there's an effect of grip strength or not. You could also talk about the values of grip strength at which there's an age effect. So you'd have two different sets in the same way that you could talk about one as the moderator and the other as it. It's just that if the other one is a grouping variable, there's a limited set of possibilities, so this doesn't make any sense. So these are two-way interactions, right? Have we done any two-way interactions in class yet that you can think of besides this day? Yeah, Aaron, what are you thinking of?
It was like
Time by time, right? So you've seen that. What if I wanted to look at predictors of individual differences in quadratic change? Could I do that? If I did that, that would be a three-way interaction, right? Right? Do you know what to do with a three-way interaction? No. Hope it's not significant. Is that the right answer? Well, guess what, folks? We're going to have three-way interactions pretty quickly. So let me do those. Same idea. If the two-way interactions move the main effects around, making them more positive, less positive, more negative, or less negative, the three ways move the two ways. The three-way interaction describes how the two-way differs as a function of a third variable. So there's three possible ways that could go. So for example, let's do the algorithm here. If I have a main effect of x of 1, a main effect of z at 0.5, and a main effect of w of 0.2. Those are going to be my conditional main effects. This model has all the possible interactions up to the three-way in it. So let's talk about how we would talk about it. Focus first on x by z. This is my two-way interaction. Because I have the three-way interaction in the model, this holds specifically when w is 0, the third variable. So for every 1 unit change in x, I would say the capital. I don't want to think I'm yelling at you. The slope of z becomes, these are all positive numbers, folks, more positive, by the interaction, 0.1. If I go the other way, for every 1 unit change in z, the slope of, I gave it away, x becomes more positive by 0.10. Likewise, if x by w is 0.01, that's specific to when z is 0. So if I want to talk about for every 1 unit change in x, the slope of w becomes more positive by interaction term. Copy, paste, change, x. Let's do it again. Z by w, specific to when x is 0. For every 1 unit change in z, the effect of w becomes more positive by that interaction term, 0.05. For every 1 unit change in w, the slope of z becomes more positive by the interaction term. Now the three-way. Isolating one variable as the moderator, talking about what happens to the two-way interactions. For every 1 unit change in x, the slope of z by w. Three ways move the two ways. Becomes more positive by 0.001. I'm going to copy, paste. For every 1 unit change in z, this has to be then x by w. And last but not least, for 1 unit change in w, this needs to be x by z. So for all of these then, you just have to look at the direction of the effects and figure out if you're in a more positive, less positive, more negative, or less negative world. Note that the coefficients are tied specifically to this idea of a 1-unit change. So you can't say something like, the slope of W becomes more positive by 0.01. It's per unit change in the moderating variable. So the coefficient is tied to a unit. So if you're going to put the coefficient in a sentence, you have to remember the unit part that goes with it. There, put on the whole screen there. Is this getting easier? Getting repetitive? I'm aiming for righteous boredom. Do you know what that is? Because there's boredom and then there's righteous boredom. Righteous boredom is like, I get it, yeah, can we move on? Righteous boredom. That's what we're going for here. So let's practice some more. The formula to get the simple main effect of each of these variables in this model that has every two-way and the three-way interaction. Come on. There we go. Simple effect of x. I got to pick out all the terms that have x in them. So I'm typing fast here. I need a beta 1, right? Do I need beta 2? No. Do I need beta 3? Do I need a beta 4? Yeah, beta 4 by itself or beta 4 tied to something? Tied to W. Yeah. If I pull the x out of here, I got to keep the other stuff that's attached. Do I need beta 5? Yeah. Beta 5 tied to Z. Do I need beta 6? Nope. Do I need the three-way interaction? Yes. Beta 7 times what? Yeah, the stuff that's not X, right? We have a Z and a W. Here, I'm going to shorten these to be B's instead of betas. Forgive me. I'm trying to keep it all on one slide. Now let's do it again for Z. I'll start you off. I need a beta 2. Anything with it? Nope, just one of those. Do I need beta 3? Do I need beta 1? No. Do I need beta 4? Do I need beta 5? Do I need it attached to anything? X. Do I need beta 6? Yeah, I need attached to W. Do I need beta 7? I'll give you a hint. I will always need beta 7 because it has everything in it. So the only question is, what does it get attached to, right? Since I'm talking about Z, I only need the X and the W this time. I'm going to copy paste here so you can see the pattern. Now I just need, for W, I need a beta 3. Its interaction with X, which is beta 4. I need its interaction with Z, which is beta 6. There we go. And then I need X and Z here instead of W. So if I were writing out an estimate statement then, I would have, for the last one here, W1 plus X by W, and then the value would be whatever I want for X, plus W by Z, the value would be whatever I want for Z, and then x by w by z, and then it would be whatever I put here for x and z multiplied together would give me the value. So I can get the predicted main effects for any level of the other variables. And this also sort of shows you why it is that these simple main effects are interpreted the way they are. When is the only time that the simple effect of x is just beta 1? When everything else goes to 0, right? And the only way that would happen is when x is 0 and, or not x is 0, excuse me, when w is 0 and z is 0. Otherwise, it's going to be beta 1 plus something. Now let's do it again, but for the two ways. I want to know what x by z is predicted to be for different kinds of people. So do I need beta 0? No, I don't need beta 0 at all on this page because I'm predicting simple slopes, not outcomes. Do I need any of the main effects? Nope. If I want x by z, I'm only picking out the stuff that has an x and a z in it together. So there's its simple two-way interaction, right? Beta 5. I don't need this one because I don't have an x and a z. I don't need this one because I don't have an x and a z. I do need this one, right? I need a beta 7. What is it attached to? W. Copy paste. If I want to do it again for x by w, I need x by w by itself. That's beta 4. And I'm going to need my beta 7 times z. And last but not least, that one is beta 6 times the missing letter. I'm losing my mind here. X. Oh, I'm starting to see some righteous boredom, I think. I like it. What would happen if I had a four-way? More stuff on here, right? But ultimately, the two-way interactions would have some three-ways in the four-way. The three-way interactions would have the three-way plus the four-way. The four-ways would be unconditional. So you can pull these apart and using the same logic no matter how high up you get. At some point, it gets hard to put it into words, and that's where pictures are very, very helpful. So here's your summary here. Interactions are moderation. Main effects change interpretation and coefficient once they are part of an interaction term. The highest order term is always unconditional. So predicted outcomes. I want to talk about this last here since we're almost out of time. To make the picture, right? If I'm stuck with a four-way interaction and I want to make some kind of sense out of it, right? I can write a million estimate statements and I could write like 3 pages of text, but ultimately I'm going to need a picture to point at. How do I get the dots that go in the picture? Here are 3 different options for you in most to least painful. The first way, and on the Piles of Variance website and throughout my course materials, I give you Excel spreadsheets by which I made all my pictures. Not because I like doing that, but because I think it's useful pedagogically to get you used to the idea of writing out an equation to generate a predicted value. Intercept plus slope times variable plus slope times variable plus slope times variable. Those will give you predicted values. You won't get the standard errors for them, but you can get the predicted values and you can put them in a picture. You can also do programming statements. And so that is like what we did, which slide was that here? Like this one. I could write out 1 line for every dot that I have to predict to describe my four-way interaction. That would be a lot of lines. The advantage of that is that you get your standard error with it, so you can do your confidence intervals. It can be tedious in certain software programs, and that's, by the way, where Stata wins hands down. Margins, have you seen this? Like, you can say margins this to this, range this to this, and it does all possible combinations with one line of code. It's beautiful. I don't know how to do that in other programs. But the solution that I have figured out in other programs, I don't bother to do this in Stata because it has that option, but in anything else, the world of fake people. Have you seen this before? You're nodding. You seen this? Out of my book, yes, fake people. So this idea works really well in situations where you're not sure what your model's going to look like, but you know you're going to have to run like a lot of iterations to get to the point where you have a final version, and you don't want to write out an equation every single time your model updates. You make literally fake cases and add them to your data set. You give them the values of the predictors that you want to plot. So I make up, say, a person who's an 85-year-old man and an 85-year-old woman. I make up an 80-year-old man and an 80-year-old woman, and I make up a 90-year-old man, 90-year-old woman, whatever. I give them every combination of predictor values. I figure out how many occasions they need if it's longitudinal. I figure out how many unique combinations I need if it's like, for instance, like if I have a three-way interaction, at a minimum I need 8 people because I need high and low on each of the 3 variables in all combinations. If you wanted to do high, low, and medium, that would be 3 to the 3, 27 people or something. You add these cases to your data set that have the predictor values. You don't give them outcomes. You run the model on your combined data set of real people and fake people. Do you remember the rule about missing data from like day 1? Does multi-level modeling or any other linear modeling program handle missing data? It kicks out any rows that are incomplete. So your fake people aren't actually going to get included in your model because they don't have outcomes. So you're not messing anything up. But there is an option that you can add on the model line in SAS and on the save line in SPSS. It's like outPM equals in the name of the data set, or save equals fixed pred in SPSS, and it adds it to your current data set, by which the model will generate predicted outcomes for all people in the data set, even if they weren't in the model. So the model then writes a new column in your data set that says what their predicted outcomes are going to be. You then take just those fake cases and you plot them. So it's super convenient if you have a complicated model or models that are going to change, or let's say you have something like where you have 10 different outcome variables and you want to look at the same predictors for all of them. Do you guys ever do data analyses like that? No one's willing to admit it, right? Everyone has that person working with them. It's like, I have 10 outcomes. I want to see how it relates to all this stuff. Well, here's a fast way to do all this, folks. Don't tell them I told you, okay? Because then you can pretend like it took you way longer, and then you can use the rest of your time to your advantage, like to, watch pirated YouTube videos or something. I don't know. Take your data set. Remember stacking that we did in homework 1? You write a new line of data to change your data set from wide to long. You can do that for DVs. So if I have 10 DVs like this, I could write 10 sets of proc mixed codes, right? But that would be annoying. No, I'm going to take my 10 DVs and I'm going to stack them this way into one data set. And then I'm going to run proc mixed the same as I normally do, with one critical difference by DV. It will then spit out all 10 versions of the same model, one for each DV. So it will run all of your analyses at the same time. And if you have, say, 10 sets of predictors that you want to include, so you would be like 100 models, take your stacked data set of 10 DVs and stack it again with your 10 IVs, and then go by IV DV, and it will spit out 100 models. Boom. You don't look impressed. You should look impressed. Okay, that's good. And all of the little tables that I'm teaching you how to save, they all have the DV in them. So you know what was significant for each DV. So these are tricks that you can use to work these programs to your advantage. So in the example that we will start next time, I start off with an entry of fake people. I gave them an ID of -99 for two reasons. It is unlikely that a person ID variable would ever be negative, but also when I sort by ID, they'll be first. That way I can grab them easily and make sure that I don't confound them with my real data. So I give them, in this example, values of grip strength and age, and I held their other covariates to 0, and I'm going to include them in all my models so that they get predicted values that I can then stick in pictures. So, such as this one. Here's a portion of the data set where they have their predicted column, and then there's my picture I made in Excel with these predicted values. So that's what we'll do next time. More practice with interactions, hooray! So I shall see you next week. Office hours start now.